Assalamualaikum and very good afternoon. Alhamdulillah, Allahumma salli ala Sayyidina Muhammadin wa ala alihi wa sahbihi wa barik wasallim. In previous video, we have learned on how to evaluate the limit at infinity. So in this video, we are going to learn about the continuity. So a function can be divided into two categories, which are continuous or not continuous, which is discontinuous. Continuous function flows nicely in smooth direction without interruption. Meanwhile, the opposite pattern are observed for the discontinuous function. So one of the easy way to detect the continuity of the function is by looking at the graph. If its graph can be drawn without lifting a pen or pencil, then the graph is said to be continuous. Meanwhile, if the graph is break or there exists the hole, so means that the graph is discontinuous or not continuous. So we will discuss the continuity of the graph in the next slides. Continuity of a function. Okay, two figures here shows the comparison between the continuous function and not continuous function. So for continuous function, as we can see, the graph is sketched without lifting a pencil or pen. Meanwhile, for not continuous function, the graph is break, which means that it is not smooth. Example. Determine the continuity of the following graph. As we can see, the graph, let's say it starts from minus infinity. Okay, start from infinity, moving forward, okay, to 0, and then moving forward to infinity. So the graph is continuous, which means it's not broke, it's not break, okay, at any point of x. Different with this example, okay. So this graph is break, okay, it's break at x equals to 0. Okay, so means that this graph is not continuity at x equals to 0. The continuity test. So a function is said to be continuous at point, let's say x equals to c, if the following conditions are satisfied, which is the first one, the function f is defined at x equals to c, which means that fc is exists. Second, limit for fx as x approaches c exists. And the third one, which is the very important one, is limit for the function fx as x approaches c is equals to fc, which means that 1 is equals to 2. So failure to meet one of these conditions, then the function is discontinuous or not continuous at x equals to c. So if you want to test whether the function is continuous or not, we must find the value of fc, and then we must find the value of limit fx as x approaches c. If the value is same, then we can say that the function is continuous. Okay, example, determine the continuity of the following graph. Okay, so we first define the limit for fx, okay, as x approaches c. So we get this point, okay, and then we find the value of fc. So fc, we also get this point, mean that limit for fx is equals to fc. So therefore fx is continuous at c. Okay, so this is realistic since our curve here is smooth and not break. Okay, so next example. So we finding the limit of fx. Okay, we get this one. Okay, limit for fx. Then finding the value of fc. So fc is defined with this red point. Okay, so since limit of fx is here, okay, and then fc is here, so which is not equal, so therefore fx is discontinuous at c. Okay, so as you can see from the graph also, the curve for this function fx is break at c, which is means that it is not continuous at c. Okay, so next example, so finding the limit of fx, okay, approach c from the left, so we have our left side limit is this point, and then approaching c from the right, then we have right side limit is here, so means that our limit does not exist. So since our limit does not exist, means that it is not continuous at point c. Okay, so lastly, quite similar with the previous example, okay, so limit from the left is here, okay, and then limit from the right is here, means that limit does not exist, therefore fx is not continuous at c. Okay, so let's move to another example. Determine whether the function of fx, which is equals to x squared minus x minus 2 divide x minus 2, continuous at x equals to 1. Okay, so by using the continuity test, so first we define the function of fc, which is f1. Okay, so straightly forward, substitute x with 1, okay, into this function, then we get f1 equals to 2. Next, we define the limit for fx. Okay, define the limit of fx. We can use the analytical method, substitute the value of 1 into x, then after operational, we get limit for fx as x approaches 1 is equals to 2. So comparing the both result, since limit for fx where x approaches 1 equals to f1, which is equals to 2, so therefore we can say that the function of fx is continuous at equals to 1. Next example, determine whether the function fx, which is equals to x squared minus x minus 2, okay, so this is the similar function, okay, is continuous at x equals to 2. Okay, so first we use the continuity test, define the value of fc, which is f2. So when we substitute x equals to 2 into a function, then we get undefined value, okay, which is 0 over 0. Okay, so next we find the limit of fx as x approaches 2. Okay, so first when we substitute x equals to 2, then we get 0, okay, 0 over 0, which is indeterminate form. So what we do is we move to the factorization step. Okay, so we factorize the numerator and the denominator, then we get x minus 2 multiply with x plus 1 divide x minus 2. Okay, so after we cancel out common factor, then we only have limit x plus 1 as x approaches 2. So substitute x equals to 2, we get 3. So limit fx equals to 3. So when we compare, okay, we can see that the limit of fx as x approaches 2 is not equal to the f2. So therefore, we can conclude that the function of fx is not continuous at x equals to 2. Okay, so here discuss the continuity of piecewise function at x equals to 0. So we have three functions here: x plus 1 for x less than 0, fx equals to 1 for x equals to 0, and then sin x over x as x greater than 0. Okay, so first we find the value of fc, okay, which is f0. So f0 is clearly determined here, okay, which is equals to 1. Okay, so next we check the existence of the limit. So we need to evaluate limit from the both side, because we have left side limit and the right side limit. So by using the numerical approach, we obtain, okay, so this table. So approaching 0 from the left, okay, we see that it is approaching 1. Okay, and then approaching 0 from the right hand side, okay, for the function of sin x over x, we also get 1. Okay, so means that our limit, okay, since our left side limit and the right side limit is equals to 1, therefore our limit is 1. So comparing our f0 and our limit, okay, so we have a same value which is equals to 1, so therefore we can conclude that the function of fx is continuous at x equals to 0. Okay, so next example, we have a given fx equals to sin x over x. Okay, so this is quite similar function with previous example. For x not equals to 0, okay, and then we have fx equals to k as x equals to 0. Alright, so this question is quite reversible with the previous example. Okay, so they did not ask us to find whether the function is continuous or not, but they asked the value of k so that the function is continuous. Okay, so find the value of k so that the function fx is continuous. Okay, so when the function is continuous, the most important information that we have is the f0 here must be equals to limit of fx as x approaches 0. So I repeat, when the function is continuous at x equals to 0, the f0 is equals to limit of fx as x approaches 0. Means that this both value is exists. Alright, so f0 directly we can take here is actually equals to k. Okay, so here we have another information, f0 equals to limit fx, which is equals to k. So we can calculate the limit fx. Okay, calculate the limit fx by considering the previous example. When we calculate the limit of sin x over x, we get 1. Okay, so here we just simply put limit sin x over x equals to 1. So since f0 equals to limit fx, which is equals to k, and the limit fx itself is equals to 1, so directly we have k equals to 1. Okay, so lastly we have an example, determine whether the function fx is continuous, okay, by using continuity test. So first we determine whether it is continuous at x equals to 1. Okay, x equals to 1, here is 1. Okay, so defining f1, refer to the graph f1 equals to 0. Okay, so next, finding a limit. So limit for fx as x approaches 1. Okay, so we consider from the left side. So as we can see, the graph approaches 0. For the right hand side, okay, as x approaches 1 from the right, okay, so it is also approaches 0. So since we have, okay, limit fx on the left and limit fx on the right is exists and same, therefore our limit fx as x approaches 1 is equals to 0. Alright, so now we compare these two information, which is f1 equals to 0 and limit fx is equal to 0. So by comparing this, since limit for the function fx as x approaches 1, which is equals to f1 equals to 0, therefore, or hence, we can say that the function of fx is continuous at x equals to 1. Right, so I hope that all of you can try for the continuity of the function fx at x equals to 2 and x equals to 3. Alright, so we have covered all of the topic in chapter 1, starting from the concept of limit until this topic of continuity. Alhamdulillah, thank you very much for your interest. I hope all of you enjoy this lesson. Till we meet again, Assalamualaikum and a very good afternoon.